Sorry about that. Google Slides turns out not to be great. OK, thank you so much for that introduction. I'm definitely going to be the odd one out in this session. We're going to be talking about mutable state. I think the rest of the talks cared much more about purity. But I think what joins us all together is we do love our pure functional languages at ICFP. We like that they're grounded in mathematics. They have nice equational reasoning principles. But sometimes we might want maybe a little bit of mutable state. Maybe we want to implement, I don't know, some sort of mutable counter or do something a little bit more efficiently. And when we combine simple mutable state with pure functional languages, we still have nice models and nice equational reasoning principles. And a lot of our meta-theoretical properties of the original functional language still hold. And then you might think, well, what if I can extend this a little bit? What if I try to add functions on the heap? Maybe just simple, pure functions. What do my models start to look like? And oh my God, what happened? Why did everything get so complex? Now, this is all past work. And what past work is trying to do is essentially model the hardest kind of reference, which is higher order references. So mutable references to functions that themselves mutate the store. And it turns out this space is very complicated and almost continuous, and so models need to find a way to impose some sort of structure. So we might do that using step indices or later modalities to try and get that structure back and try to use our favorite proof technique of induction, really. And so in this paper, we take our pure functional language, and we want to add higher order-ish mutable state. So functions aren't completely unconstrained. Otherwise, we end up with a model that looks like this. But we have still a simple model with higher order references. And we still have our meta-theoretical properties of our original functional language. In particular, we prove termination. And we do all of this using type universes. Now, we saw an earlier talk about type universes. They're used in dependent type theories to sort of lay out the types along a hierarchy. I won't get into the details from the dependent type theory side, but you'll see how our type universe hierarchy emerges later. So the plan for this talk is to spend quite some time on background, in particular on possible worlds models for modeling languages with mutable references. We then encounter the type world circularity, which is the source of all that complexity we saw in that earlier model. And then we'll talk about what this work does, which is using type universes to distinguish allocations, avoid the complexity from the type world circularity, and describe a new space of higher order references. So let's start with talking about possible worlds models. So we're talking about modeling the behavior of languages with mutable references. There's kind of three main ways that a program might interact with the heap. We want to allocate values on the heap. We want to read them back. And we want to update these values on the heap. This is all very concrete behavior. We want to abstract this behavior. And this is what we do in a possible worlds model. We use a world to represent our heap. And it's sort of an abstract heap shape. This allows us to sort of prove more things about our program, have more equations hold, because then we can kind of prove things under any possible heap shape rather than concrete heap. So this is all very vague. Let's kind of make this more concrete. And look at the behavior of this program. We don't really care about its final value, but let's just look at its effect on the heap over time. So initially, the heap is empty. Then we perform an allocation. So R is mapped to 3. We might update that value and then perform another allocation. Now, the world that corresponds to this heap is going to follow a similar structure. So we start off with an empty world. When we perform an allocation, we want to note down that we've performed this allocation and what possible values we can store in this location. So in this case, we can store things like natural numbers. You can almost kind of think of it as like typing the heap. And then later, when we try and update a value on the heap, we can easily check that this makes sense, right? The location exists, and we're updating it with a value that makes sense. And then as we go along and perform more allocations, we make sure to record these down in the heap. OK, this has been far too long on mutable references. We're at ICFP. We care about functions, right? So how are functions represented in these possible worlds models? So here I've filled out my program a little bit more. I have a function f, Doesn't matter what it does with this parameter, so I kind of just indicated that with an underscore. We're actually just going to get whatever value is currently stored in R. And then later I'll call this function on a natural number. And so we kind of see that functions have a sort of temporal nature as well. There's a point in time when a function is defined, and a different point in time under a different heap at which the function might be invoked. We see this a lot more clearly if we kind of look back at our timelines. So the heap and the world have a particular shape and look at the point that f is defined, and it's similar but still different when the function f is invoked. Now, in this particular case, we're lucky. We know exactly the point that f is defined and when f is invoked. But in general, we don't know when f might be invoked, and we don't know if we might have multiple invocations of a function. So we need to kind of build in the notion of a future when representing function values in possible worlds models. So I won't get into actually the technical details, but the idea of how we represent values in possible worlds models is we describe them as behaving, so like the function f will behave like a not-to-not function in all future worlds from the current world. Later on, when we invoke this function, it becomes very easy to check that everything lines up. We check that, of course, the arguments line up, but then we also can check that, hey, does the heap state still make sense? Okay, so that was very quickly about possible worlds models. Just to quickly recap, world is sort of abstracting the heap. It's showing that it's recording down allocations and what those allocations can store. When representing functions in possible worlds model, we need to build in this notion of the future in our function values because they may be invoked at different points in time. So let's continue down our path. So we've seen mutable references, and we've seen functions and how they're represented in possible worlds models. Can we just kind of smash them together and get a model for higher order states, so allocating functions on the heap? So here I've changed my program a little bit. Now L is actually going to allocate the function f. And so based on what we've seen so far, right, we're going to allocate this function f onto the heap. L is going to map to this function. And based on what we've seen so far, we would think, well, we need to note down what kinds of values can we store in the location L. Well, f is a not-to-not function, so we might think, well, that should be what we can store in L. But unfortunately, it turns out not-to-not is not enough information. In particular, we don't even know that our initial allocation is safe. To know that our initial allocation is safe, we need to know what R is always storing. To know what R stores, we need a world. And additionally, we might have later allocations. We might update L with different functions that rely on those allocations. So in general, to describe the kinds of values that go into L, we need a world to describe them. Okay, so zooming in, we're trying to describe what kinds of values can L store. We need some notion of worlds, but there's kind of two different worlds going on here. There's the world at the point in time that f is defined. We'll call it world 1. And there's the world that's defined when f is allocated. We might think that, well, we already have this kind of notion of future worlds, so maybe we can describe the values in L as saying, well, in all future worlds from world 1, I'm going to store functions that behave like not-to-not. But future worlds of world 1 include world 2, which contains L, which I'm trying to define right now. And if you're confused, great, so am I. This is exactly the point in time where we kind of hit the type world circularity. So the problem is we're trying to define worlds in terms of themselves, in terms of worlds. And this becomes a lot more clear if we look at the semantic equations. So in describing a world, we're mapping locations to types, but types need a world to give us back a set of semantic values. So we kind of have two possible options when using possible worlds models. On the one hand, we can simply just store simple data. This is easy to model, but our resulting language isn't very expressive. On the other hand, we can store functions. We get very complicated models, but a very expressive language. But I want more hands in the middle, right? I want to store different kinds of functions. Remember our little guy at the beginning? You know, what if I want to just allocate simple, pure functions? What does a model for that look like? So this is where type universes come in. So we used type universes to distinguish allocations. What we mean by that is we distinguish, our kind of tagline is we distinguish future allocations from the perspective of past allocations. Now, what do I mean by that? So let's look at a particular allocation R, allocating the value 3. And we want to distinguish R as a future allocation with respect to its value. Now, the value here is 3, so it's not really an allocation, but you can imagine that we're allocating different references or functions that might rely on other allocations. And so we need a way to distinguish things like 3 from things that store things like 3. And I think most of us are type systems minded here, so things like 3 are like nats, right? And things that store things like 3 are ref nats. But we want to go beyond just storing natural numbers. We want to store functions, other references. And so we need to classify our types into different levels. And so for any given type level that our type might be in, the reference to that type level is going to live in one level higher, type I+1. So in our language, we actually end up with a kinding system over our types. So for any type at a particular level, the reference to that type is going to be at level I+1. Now, how does this look in our semantics? Well, it turns out that this distinguishing in our kinding system corresponds directly to distinguishing worlds by allocations. So here I'm going to give you a world, and I'm going to actually pinpoint the times at when I perform allocations. So at this point in time, I perform the allocation R to store the value 3, a natural number. But I want to remember, I've kind of like added this weird bend in a different color, right? The reason is because I want to remember what world I had previously. It was the empty world. It's not super interesting. Let's see some more allocations and get a little bit more interesting. Before I perform an allocation, though, I do define the function f, which dereferences R, so it relies on this allocation R. Then I perform the allocation L. I'm going to allocate L to store the function f. And so again, I want to do the splitting where I say, continue this world with L in it, but also continue the world that had R allocated without L allocated. So zooming in on this last part, I haven't given you the description of the values that L can store, functions like f. Well, functions like f depend on this level where R is allocated, so I'm going to call that level I. And I'm going to describe the level where L is allocated as level I+1. And so when I describe values that can be stored in L, I'm going to describe them as values that rely on future worlds of this lower level, level I, not all possible future worlds. So in particular, we say that f behaves like a nat-to-nat in all future worlds of level I, and that does not include its own allocation L. So we don't encounter the type world circularity at all, which is quite nice for our model. Now, popping back out, thinking about the universe of functions. Here I have a completely new program. Here I'm going to allocate the identity function in the reference R. And then I'm going to have f rely on that allocation R again, but we're actually going to apply whatever function is in there to just the nat0. And so based on how I've typed this and based on your knowledge of type systems, you might think, well, both of these functions are usually considered nat-to-nat functions. But now with our distinguishing allocations in our worlds, we see that they have very different semantics. So at the point in time when the identity function is defined, the world is empty. It relies on no allocations. Then we perform the allocation of R, we split our worlds, and we see that the definition of f relies on the allocation of R. And so really, f relies on future worlds at level 1, whereas the identity relies on future worlds at level 0. And so the nat-to-nat type is actually not enough information to distinguish these semantically different types. So just to recap, the identity function here relies on no allocations, whereas f depends on the allocation R, which is a future allocation with respect to the identity function. And so we distinguish these functions in the syntax by annotating our function types. So the identity function is going to be annotated with 0, and because f depends on type level 1, it's going to be annotated with this 1 on the arrow. And so in our little language, we have a typing rule that's kind of the same typing rule you might expect for functions, but now we have this index that we have to determine. We kind of coarsely determine this by the context, just for ease, but this is obviously not very practical, so we talk about how to make this more practical in a language implementation. And so we end up in our language with a type universe hierarchy that kind of starts with base types at type level 0. As we perform allocations of those base types, we then move into type level 1, type level 2, etc. So in the semantics, again, if we look at our semantic equations, we see that the world is now defined in terms of worlds at lower levels. So the world definition no longer contains itself. And for those of you who might know a little bit more about possible world semantics, we do have a notion of future worlds, and it's actually defined as a product over these leveled future worlds. And the semantics of functions are defined over these leveled future world relations. And of course, there's never enough time for these things, so I will briefly touch on a little bit more what's in the paper. So we actually find that this distinction between past and future lets us distinguish between references to other references, which I haven't mentioned at all. And we can actually distinguish between saying, a reference to another reference that could be possibly cyclic is sort of a future, kind of quantifies over the future, and a reference that points to another reference that definitely doesn't ever point back to itself is only allowed to quantify over the past. So then we can really distinguish between cyclic and acyclic references. So just to quickly recap, type universes turn out to be quite useful in our semantics for distinguishing worlds based on allocations. This enables us to store different kinds of functions. We saw those functions laid out according to the hierarchy. And we get a nice simple model where we don't encounter the type world circularity. And in the paper, we show that termination holds in the presence of these higher order references. So thank you very much. I have a talk actually directly after this next coffee break at the workshop iWACO, where I kind of talk about future work, how this might apply to memory management. And there's a bunch more talks from my group if you're interested in those. Thank you very much.
Am I on? Yep. I would like to invite anyone with questions to please queue up at the microphones.
So if I understand right, the main thing you disallow in the example is that you make the identity function, you put it in a reference, then you make a new function that reads from it. And if the type of that second function was also A to A, what you disallow is then putting this function into the reference that is read by the thing. Is that a fair summary of? Yeah. Yeah. So my question then is, do you have any examples or any intuition for the kind of programs that would be useful but are disallowed by this? What do you lose with this kind of safety?
Yeah, that's a good question. So what kinds of programs might be disallowed? I haven't studied this super extensively, but there are some techniques for sort of introducing recursion, like memoizing computations and things like that. So that would be disallowed. So that might be not desirable if that's something you want. So some more efficient programs might not be allowed. So
memoization of something where the thing you compute is itself a function, you mean?
Yeah, if there's some sort of computation that you're kind of trying to backpatch, yeah.
Okay, thanks.
So you wouldn't have Landon's not?
No, you wouldn't have Landon's not.
Okay.
Hi, Max New, University of Michigan.
Could that be?
So watching your explanation, it reminded me of typed closure conversion. The circularity, it seems a lot like the impredicativity that's required in typed closure conversion. And so the solution looks a lot like if you only had predicative quantifiers. So is there a precise relationship there?
I don't know about a precise relationship, but this was definitely inspired by that. We were looking at closure conversion and we kind of saw, oh, this is actually necessary, this impredicativity. What if it wasn't? And what kinds of expressivity do we get? Okay. But yes, this is a very, very good observation.
Yeah. And then can I think of the universe level as like a kind of region, right? And this is kind of like a stratification of the regions.
Yeah, did I plant you in here? That's what my next talk's all about. Yeah,
okay.
yeah. So you can kind of think of them as regions. They're obviously really bad and big regions. So I talk about in my I
So I
walk
just
talk.
want, if you have compared it to region calculi at all. If you
I
looked into that.
mean, not directly, but I think there is a representation that we could make, yeah.
Cool, that'd be nice.
Thanks.
Remind everyone that monetary transfers for questions are not allowed.
Oh,
You go ahead.
Yes, so this may be a stupid question, maybe, but so you mentioned that you don't have Landis nots, so do you have termination?
yes, yeah, we do prove termination. So this is a nice property, like for these kinds of higher order references, you can get termination, and then hopefully, you know, you can use automated reasoning tools over that kind of subset of programs. But if you wanted non-terminating programs, you could always add them back in using fixed points or anything like that, right?
Hi, is it on?
Yeah?
Alejandro Aguirre, University of Aarhus. So there was a very recent paper at, I think, PLDI, with a logic called NOLA, which presents like a version of separation logic without laters, and then they have like a stratified universe of propositions.
Okay.
It seems like very related, but I don't know if you...
I have not seen this,
looked
so
at it
that's a
or-
great reference. I'll talk
Okay.
to you after and get that. That sounds great. Thank you.
Any more questions?
Sit down.
Okay, wait,
Did you
I'm
come to Singapore to
I'm
open a bank
confused.
account here? Is that the idea?
Well, I'm confused about something, okay? So the solution you show, it looks a lot like the way that we solve recursive domain equation with step indexing, but with those models we still get a non-terminating language. So what's the difference between the way you resolve the domain equation and the normal step indexed approach?
Right. So then in the syntax, we actually enforce that the functions follow the stratification as well, right? So if we didn't have these annotations, so let me go back to this example. So if we didn't annotate these function types, right, we would have that they're both nat-to-nat functions, and then you could sort of backpatch and do Landon's not if you updated the reference R to contain F, right?
Okay.
And here we say, well, they're two different types. One's a 0 type and one's a 1 type. And so we've enforced that now in the syntax.
So should I think of the normal step indexing as these are all interpreted as like omega functions or something like that?
Yeah.
Okay,
I think you could.
But then the models themselves are kind of very closely related.
Yes, yeah. I mean, I see Amal in the audience. I mean, Amal talked about trying to stratify it based on syntax, but then, you know, wanted to represent quantified types. And so, yeah, this is kind of the approach that Amal did not take.
Thank you.
Are there more questions this side of the room?
Yes, please.
You can still create the cycles. This is preventing the cycles from
Yes.
ever being created. Right,
Oh, yeah.
exactly.
Thank you.
Dominique?
I'm curious, there's a recent paper by Nick Swamy about sort of avoiding step indexing by having this sort of hierarchy of propositions. Is this related? Could you model
Nick
your
and I have
type
been
system
talking,
there?
yeah.
Sorry?
Yes, Nick and I have talked about this before, yes. So it is related. Yeah, because in F-star they have a predicative universal hierarchy, and so then they can't actually, like, they have some trouble with representing like higher order ghost state because of this, and so this could be, yeah, possible.
Yeah, so one thing they mentioned, if I remember correctly, is that they can't model semantic typing for interesting type systems. Maybe yours might fit, right?
Yeah, hopefully. Yeah, we should talk more.
Hello. Maybe a silly question, and I don't really know how to phrase this correctly, but like you have the branching timeline, and like on the lower like branch, does it have any purpose other than to hang around to be referenced in the future? Like, can you like branch off the lower one? Like, is it more like a tree, or is it more like just like an ascending? Because the indices are very like sequential, but like I'm imagining like in a scenario like that exists in like the pink branch where you branch off there. Like, what do the indices look like in that situation, or does that just not happen?
Yeah, I've kind of lied to you. So these levels, of course, for the purposes of the talk, right? So these levels are kind of indicating the level of the type. And so if we performed more allocations of like natural numbers, they would actually live at this lower type. And then, you know, any further allocations at higher levels, so like L is allocating at level 2, we then have it there, right? And so the branches happen at when levels increase. But otherwise, they will kind of, we talk about it as like time travel. They will time travel to the right level, essentially.
Thank you.
I'm afraid we have overrun our time, so the rest of the questions... Oh, sorry. Go ahead.
Hello, Junyoung Jang from McGill University. I have a question about polymorphism. How do you deal with the polymorphic data
Future
type?
work.
Yeah.
But great question. Yeah, we should talk.
See, your great reward for giving an extremely understandable talk is that people line up to ask questions and they can't stop. Can we thank Paulette once more, please?